If you were to rocket out into space 20 miles and then look back, the receding Earth would look like this. For the story of the hazards of Earth's radiation belts, danger that lie beyond our atmosphere, stay tuned to Science in Action. American Trust Company, for the 10th year on television, proudly brings you Science in Action, produced by the West's oldest scientific institution, the California Academy of Sciences. This award-winning series is presented each week at this time by American Trust Company, serving Northern California for more than a century. For complete banking service, visit any one of the more than 100 offices throughout Northern California. And now, once again, Dr. Earl S. Harrell.
The Earth is ringed by two zones of high-energy particles. These areas are now called the Van Allen radiation belts in honor of the physicists whose work led to their discovery. The existence of the Earth's radiation belts presents a very serious hazard to future space travel. What is the intensity of this radiation? What does it consist of? How much shielding will the first space travelers need in order to penetrate these deadly areas of radiation safely? As a result of a unique experiment, some of these questions have been answered. And to tell us this remarkable story, we've invited the two scientists who conceived and carried out this project. Our first guest is the leader of the Nuclear Effects Group for the University of California's Lawrence Radiation Laboratory, located at Livermore, California. I'd like to have you meet Dr. R. Stephen White. Welcome to Science in Action, Steve. How are you?
Thank you, Earl. It's a pleasure to be here.
I would like to know what it was that gave Dr. Van Allen the first clue to the existence of these radiation belts.
The first clue, Earl, was furnished by a raccoon.
Well, I know raccoons, but raccoon, I'm not quite sure.
Well, it's quite an appropriate name, Earl. A raccoon is made up of a balloon and a rocket hung from that balloon, and they were launched from the deck of a ship. Dr. Van Allen, back in 1953, was doing some cosmic ray research in the vicinity of the northern auroral zones. You know where the northern lights are?
Yes.
And during some routine experiments, about 30 miles up, he ran into an area of radiation far stronger than anyone had expected.
Well, at the time, did he have any idea what the cause of this radiation was?
No, it puzzled everyone. Further experiments were needed at higher altitudes than the raccoons were capable of reaching. The chance came in 1958 when Explorer 1 went into orbit, and it carried cosmic ray detectors and a transmitter designed by Dr. Van Allen's group.
Over here in this next section, we have sketched the orbit of Explorer 1, and I notice that down here it's very close to the Earth, whereas up here it's quite far apart. That is quite a distance from the Earth. Perhaps you could put that mileage indicator 200 miles at that point, and then I will put this one up here, which indicates 1,500 miles from the Earth at this section.
Well, this is what brought the first surprise, Earl. At the 200-mile level, the counting rate was just as expected. But as the satellite went to higher altitudes, above 600 miles, the radiation increased and then dropped to zero.
Well, that would seem to indicate that perhaps there was no radiation up here, and yet everything I read has said that the further you go out, the more radiation you pick up.
That's right, Earl. That's just what happens. And this left Dr. Van Allen with only one explanation. He quite naturally assumed that his detectors weren't working properly. The chance came to check this experiment when Explorer 3 went into orbit with equipment similar to that carried by Explorer 1.
And what kind of results did he have that time?
Just about the same thing. At the lower altitudes, the counting rate was low. But at the higher altitudes, the counting rate went up and then mysteriously dropped to zero.
Well, then either the equipment wasn't working properly or perhaps there just wasn't any radiation up here.
Well, as it turned out, Earl, neither was the case. And I'll show you on this next demonstration here exactly what happened. This is a Geiger counter designed on the same principle as that used by Dr. Van Allen in the Explorer flight. As we go on up to 2,000 miles, we have here with us Joe Hilson from the effects group at Livermore, who will put in the cobalt-60 source, which will serve as a source of radiation for the experiment.
That goes right at the top of the...
That's right in the middle of the belt. You'll notice the counter went up here as he stuck that source in.
Yes.
Now, I will turn on the sound here, and we'll imagine that the Explorer is mounted in, that the counter is mounted in the Explorer satellite, and you can hear the counts here, you can hear the sound, and you can also notice the reading on the meter. Now I'll start the takeoff here, and you can see the radiation mount as the satellite goes to higher altitudes. And you'll notice it gets pretty high here. It goes up just as we would expect as it gets closer to the radiation source.
This is the same thing that happened in Dr. Van Allen's experiment.
Exactly. And now we'll jump above 600 miles, and we'll see what happens when we get closer to the source of radiation.
Uh-oh, there it goes back down to zero again.
Yes. The explanation for this is that the satellite had gotten into an area of radiation so strong that the counters were completely jammed. Now we'll return the satellite back down to the lower level, away from the radiation.
In other words, it went back to zero and then came back up again.
That's right, and you can see it's still very high there, Earl. Now we'll go on down to the lower altitude yet. And you can see the counter is now working normally, just as if nothing is wrong.
Well, then it was a question of equipment which was designed to be very, very sensitive, but couldn't take the amount of radiation which was in this area way up above the surface of the Earth.
Exactly, Earl. Dr. Van Allen had run into an area of radiation far stronger than he had expected, and his counters just weren't designed to detect such strong radiation. The confirmation of this discovery came with Explorer 4. The lunar moon rocket, Pioneer 3,
yes,
went out 65,000 miles and not only confirmed these discoveries, but also found a second radiation belt farther out.
Well, to find out the relationship of these two radiation belts, we have set up over here in this next section an exploded arrangement of what this might look like, of course, with the Earth right here in the center.
You can see here there are two distinct belts, Earl. Both surround the Earth like huge donuts, with holes at the top and the bottom. Now, the inner radiation belt has its maximum intensity at about 2,000 miles out, while the outer radiation belt has its maximum intensity at about 10,000 miles.
Now, when you talk about intensity of radiation, what is this going to mean to the first person who takes off from the Earth as a space traveler?
Well, Dr. Van Allen estimated that the intensity in the inner belt was about 10 roentgens per hour, and the intensity in the outer belt was several times that. The human body should not be exposed to more than about 1 Roentgen per month over an extended period of time.
Well, obviously, then, some kind of protective material is going to be required to enable this person to make the flight.
Yes, the first traveler will probably go into orbit at something like 400 miles from the surface of the Earth.
This would be the radiation belt right here.
That's the lower radiation belt, and there are about 200 miles separating the radiation belt and the orbit of the space traveler. But to go farther out, for example, if he wanted to go to the moon, there are two possibilities. Now, let me go back to this diagram to show one possibility. That would be for the rocket to go out through one of the holes in the donut, but to come back in through one of these holes is a different problem, and it would be very difficult to do without passing through one or both of the radiation zones.
Well, then, if, as you say, he's going to have to go through this radiation belt to get back to the surface of the Earth, or perhaps even to go out, then he's going to have very, very good protective materials.
That's right, Earl. In order to determine the amount of shielding required, it was necessary to obtain more information about the nature and the energy of the particles that cause the radiation.
To find out about that, I'd like to go at this point and join one of your colleagues at the laboratory. As you know, he's a senior staff physicist in the nuclear effects group, so if you'll excuse me just a moment, I want to go over and say hello to Dr. Stanley Fredden. Welcome to Science in Action. You know, you and your colleagues there at the laboratory seem to me to have had a tremendous job in trying to figure out all the details of this radiation belt.
Well, the first step, Earl, was to figure out a method of getting the desired information about the inner belt.
I'm wondering, now you say inner belt. Just a moment ago when we were over here, we were talking about two belts, an inner belt and an outer belt. Why do you specify an inner belt?
We had good reason to believe that the radiations in the inner belt are more penetrating than those in the outer belt. So by shielding against the inner belt, you're automatically safe in the outer belt.
What kind of equipment do you need to get the data you require?
Here it is, Earl.
You're fooling. That's all. This is the entire piece of equipment?
This little stainless steel box contains what we call an emulsion stack.
Can we open it?
Here, I'll open it for you. Actually, each of these little squares is a piece of film. They may look a little different to you at first because the film we use is actually about 100 times thicker than ordinary photographic film.
Well, this is the entire unit. There are no hidden wires or transistors or anything else.
Yes, that is everything.
Well, now, in exposing this or getting the kind of information you need, you would use this then the same way that a person, he takes a camera and he takes a picture of someone. The picture is recorded on the photographic plate.
Well, we don't get a picture in the conventional sense, but the charged particles do leave identifying tracks behind. Here's an exposure which was made on a balloon flight. It shows a primary cosmic ray particle hitting a nucleus in the film emulsion.
Well, then, by studying these particles and the tracks that they make, perhaps you'd be able to identify the particles and even tell how much energy they have.
Yes, each type of particle makes its own particular track which identifies it, much as footprints identify a particular animal. I might add, however, that these cosmic footprints are only about 1/16 of an inch long on each emulsion.
Well, then, if I understand your work correctly, what you do is to place this inside of a rocket and send the rocket up, and when the nose cone comes back, you recover from it this piece of equipment and you study the various items there.
Yes, we used the Air Force's Thor-Able ballistic missile. It traveled about 5,000 miles down the South Atlantic range and for about 15 minutes was up about 800 miles, well into the region of the inner radiation belt.
That was a very historic flight because on that one it was the first ICBM nose cone that was actually recovered.
Yes, and here you see a typical picture. This balloon you see floating actually supports the nose cone which hangs below it.
I know the divers who did the work of actually recovering it, they had a very stringent training program. In fact, this photo is from an article in the August 1959 issue of National Geographic, a very good article, incidentally, telling of this work. Suppose now that this small piece of material, these photographic plates that you have, we were to expand all of these in this form here. Could you give us an idea what happens when one of these particles hits this photographic material?
Yes, actually the particles were all energies, and they came in from just about every conceivable direction. The low energy particles, for example, might come in and stop in one or two of the emulsions. However, the high energy particles would pass right on through.
Well, how can you tell, this is what I'm puzzled about, how can you tell that this one that came in here and you see it on this plate and up here you see it again, but how do you know that the two are the same?
The way we do this, Earl, is to use a numbered grid system. Here's the type of grid I mean. You see the individual squares, each with its own particular numbers. Also, you see an enlarged photograph of one of these emulsion plates. Now, when I superimpose the two, you can see the result.
That's sort of the thing that you'd have latitude and longitude when you're studying a normal geographic map.
Yes, that is correct.
Well, now, in the laboratory analysis of this sort of material, are many people involved in that?
Yes, we have 12 girls working for us who do the scanning and measuring. Here's an example of 4 of them working in the laboratory. They are scanning the emulsion plates. This one girl now is moving her plate into the approximate position to follow the track that she's interested in. Then she will put the objective down onto the plate, look into the microscope, and pick up the particular track that she's following. She follows it through this emulsion then, noting where it goes out by the grid, and then picks it up in the next emulsion.
Well, anybody who has done microscope work knows how difficult it is to follow any kind of material. So to carry this a bit further, let's assume now this has come back from an ICBM. It was in the nose cone, which is recovered. So let's take it over to the head of your processing department, Al Oliver, give this to him, and ask him what he would do with it to process it to get the greatest amount of data out of it. How are you, Al?
Hi, Earl. Well, Earl, we first print the grids on by contact printing. Then we mount these pieces of emulsion individually on pieces of glass. Then we process them in very much the same way we do ordinary photography, except that this takes a little bit longer. We take 10 days or 2 weeks for an individual piece. I'd like to show you what we see in one of these emulsions live, but first I'd like to show you a photograph of a couple of proton tracks. They're necessarily different tracks because this one has a very high energy and In fact, the measurements show that this would go 16 inches in emulsion if we had enough emulsion. But of course, the stack was only 1.5 inches across, and this one obviously went right through. This proton track section, you can see the grains are much closer together. This would stop in about 1/2 inch, and most likely does stop in the stack. Here's a proton track ending. Grains are very close together, touching each other, then come to a stop. The size of this is such that this is 3/1000ths of an inch, or about, say, twice the diameter of a hair on your head. Well, let's take a look at the microscope. I think we can get a picture. I've got a proton ending there. The only motion here is in the fine focus, which is moves the optical system up and down. The little curly tracks are electron tracks that most likely came from exposure while the motion was on the ground. The high energy tracks are all from the Van Allen belt. See the tracks of all different energies there.
Well, it's obvious to see just how painstaking this work is. I know that this is carried out with a great deal of detail. I'd like to go back right now, Al, if we might, and ask a question of Steve here. With this kind of information that you have worked out in your laboratory, what can you tell us now about the inner radiation belt?
Well, the inner radiation belt, Earl, consists of high-energy protons and low-energy electrons. These particles are trapped by the Earth's magnetic field, which is represented by these white lines. The particles make spiral trajectories around these magnetic field lines until they get to magnetic mirrors, where they turn around and return, and going back and forth for many days in such trajectories. Now, these particles are reflected by these magnetic mirrors, which act much like ordinary mirrors act for light.
Now, do I understand then that these things bounce back and forth from the North Pole to the South Pole and continue to do that?
Exactly, Earl. However, eventually the particles leak out the ends of the magnetic mirrors into the Earth's atmosphere, where they interact with the atoms of the air. They collide, stop, come to rest.
Well, as this matter of leakage, obviously this must be replaced, so let me ask Stan about that. Where does the replacement come from for this radiation material?
Well, high-energy cosmic rays, Earl, are continually impinging upon the atmosphere of the Earth. When they strike the atmosphere, they're traveling with energies far greater than anything the sun can put out. When a cosmic ray particle strikes a nucleus of an atom of air, it literally blasts it apart. Some of the secondary neutrons which are produced bounce back up and decay into protons and electrons, which may then become trapped in the inner belt. Now, these protons have about the same energy as the neutrons which produce them, but the electrons are low energy. In fact, the electrons are so low energy that they could not get through the Thor-Able nose cone and be detected in our stack.
Well, this would pertain then to the inner belt, but what about this outer radiation belt?
Well, we haven't sent a stack into the outer radiation belt, but we believe it's supplied by the sun. Great streams of particles are continually being shot off from the surface of the sun. Some of these reach the outer belt and become trapped. Others strike the atmosphere of the Earth near the north and south magnetic poles and set off the electrical disturbances which we commonly call the aurora or the northern lights.
Well, all of this information to me most certainly points up the penetrating power of these and the necessity of good shielding if we're ever to have space travel.
Well, Earl, we found the radiation intensity due to protons at 800 miles is about 1 Röntgen per hour. Combining Dr. Van Allen's data with ours, we found that the radiation intensity, where it is most intense, that is in the middle of the inner radiation belt about 2,000 miles out, the radiation intensity is about 100 Röntgens per hour.
100 Röntgens per hour, and earlier I think we said that 1 per month is about all that a person should have normally. So what do we do about this?
Well, the inner radiation belt is certainly a potential hazard, Earl, but shielding may be the answer. Any space vehicle will stop the electrons and the low-energy protons, but it will take 1 inch of lead to stop 90% of the protons, and it would take 6 inches to stop 99% of the protons. Now, this amount of weight might be excessive and prohibitive. However, if the reserve fuel of the space vehicle could be used for shielding, perhaps little additional weight would be necessary.
so that to get around the weight of the lead, which we use for shielding now, if we have the extra fuel, that might serve the same purpose.
That's right, Earl.
I'd like to go back to something which you brought to the program, which I consider to be most amazing. In fact, I'm very happy to learn about it. This little bit of material here, which is so significant. You know, compared to the excitement and the publicity connected with the manned satellite program, this little box may not seem like much. But when you stop and think of the fantastic amount of vital information that has been derived from it, and what this information will mean to the safety of future space travel, and to a better understanding of the mysterious forces which surround the Earth, then this little box takes on quite a different meaning. And gentlemen, I want to thank you. Dr. Stephen White, our thanks to you, sir, for coming to Science in Action to tell us of this.
Thank you, Earl.
And Dr. Stanley Fredden, our thanks to you, sir, for coming also to tell us of your work in this program. J. Jacobus is waiting for us on the other side of the studio. Let's join him.